We've done 3 things with impulse so far, and 3 things really that you're responsible for on tomorrow's quiz. The first thing is calculations. Calculations involving impulse. We know that impulse is a change in momentum. So it means it's really the symbol that we assign to should be probably delta P. Reflects the definition, change in momentum. We also know from our data sheet that impulse delta P is equal to F times delta T, and it's also equal to M times delta V. This is the part, in fact, that appears on your data sheet. Delta P doesn't. You just got to remember that's all equal to delta P, or the impulse. Remember that when we have an impulse calculation, it's an impulse calculation because one of 3 things has happened. We were asked for impulse. We were asked for the change in momentum, or the momentum gained, or the momentum lost, or so on. And finally, we were given a force and a time in the same problem. Sometimes some of you will look at questions and say, oh, look, there's a mass, and the velocity is changing. It's impulse. Well, technically, you're right. If there's a mass and the velocity is changing, there is a change in momentum, right? It is impulse, but it doesn't mean that you can use impulse to solve the problem. In all likelihood, you don't have enough givens to solve the problem if that's the case. You will have enough givens to solve the problem using impulse if you're asked for impulse, if you're asked for change in momentum, and if you've got a force and a time in the same question. Impulse will work. It may work some other time, but it may not work some other time. These are the situations that I think it's the most valuable at least to try using impulse. Hey, and you know what? If you do happen to try using impulse and you just can't make it work for yourself, then try something else. Okay, one of the other things you can try is F is equal to M times A, right? That wouldn't be my first go-to with one of these, okay, but it's a backup plan for you. Just a word of caution before we move on to the next thing here. F times delta T equals M times delta V. This is a pretty common mistake, right? People will say F times T equals M times, we talked about this before, M times V. M times V is momentum. It's close, but impulse is change in momentum. So we don't want to multiply M times V. If on your first written response test coming up in a couple months, you say F times T is equal to M times V and include only one of the velocities as opposed to both initial and final, you'll get the question wrong. Okay, I guarantee you on that test, you're going to get that question where you have to include both V's. If you don't, you're wrong. Okay, don't make that mistake. Don't be that person. All right. The next thing we looked at was qualitative impulse. And by qualitative impulse, I mean the 2 situations that can be not mathematically described, but just in concept described by impulse. The first situation is when we have what I call a predetermined impulse. When I have a predetermined impulse, when does that happen, by the way? When do I have that predetermined impulse? Yeah, Daniel? Yeah, when you're stopping something, or at least trying to stop something, right? When you're stopping an object. Maybe the car is stopping, whether it's at a stop sign or against a cement wall. Maybe the baseball is stopping, whether it's against your head or whether it's against your cradling baseball glove. Maybe you're stopping when you jump off of a desk, whether you bend your knees or not. It doesn't matter, the impulse is predetermined. When I jump off of a desk, if I bend my knees or if I keep my legs straight, the impulse experienced by my body is exactly the same, no matter whether I bend my knees or not. What's not the same? What's not the same, Rosie? Yeah, the amount of time that it takes. The impulse doesn't change. Typically what I try to do, unless I'm trying to hurt myself, is increase the time that it takes to stop. If I jump off the desk and bend my knees, I'm increasing the stopping time. So what? So what? Who cares if I increase the stopping time? Does that have any effect? Not on impulse, it doesn't. The impulse is going to be the same no matter how you stop. So changing the time has to affect something else. What is it that it affects? Force, right? If you increase the stopping time, you're going to decrease the force. That's typically what we want to do. There may be the odd situation out there where you want to decrease the stopping time to increase the force, but that's not usually the case. All right, the other situation is, said yesterday, that non-existent word, but I like it. When we have a non-predetermined impulse. When do you have a non-predetermined impulse? Yeah, yeah, when you're starting an object. Now, it doesn't mean you're starting it from rest necessarily. Yeah, a golf ball sitting on a tee is certainly starting the golf ball from rest, but a baseball coming towards you or a hockey puck coming towards you is already moving. But you're trying to start it moving in another direction or start it moving faster or something, right? When you start it to do something, then it's a non-predetermined impulse. Here, nothing is staying the same. Here, if I increase the time of contact, then the impulse will increase. But if I increase the force, the impulse will also increase. So in the first situation, impulse is the same, and force and time affect each other. In the second situation, the impulse isn't the same. Force and time don't affect each other, rather they both affect the impulse. Usually we're trying to give it more impulse, but you know there's times, right? You're throwing your curling rock. Anybody curl here? You throw a curling rock, you're not necessarily trying to give it as much impulse as possible, otherwise it ends up going right through the house and then it's out, right? So usually you're trying to give something as much impulse as possible, but not always. Bottom line is the force and the time combined don't affect each other. The force and the time combined affect the impulse that I give the object, whether it's the baseball or the curling rock or whatever. And finally, the third thing that we did yesterday, third thing that we did with impulse over the last couple of days is our graphs. And those graphs that we see involving impulse that will be on tomorrow's quiz are force versus time graphs. When you see a force versus time graph, there's three words that I want you to think of right away. What are they? Right now. Just say them out loud right now. Area equals impulse. Area equals impulse. Area equals impulse. You automatically think that. Okay, I don't care what you're asked. In fact, I don't even care if you read the question right away. Okay, as soon as you see the graph, I want you to think area equals impulse. Got it? Now, if it's a triangle, you can find the area by 1/2 base times height. If it's a rectangle, it's base times height. What if you got a triangle and a rectangle? Like, what if it's kind of an odd-shaped thing like this? Is it? Yeah, do the triangle, then the rectangle. Do them both, and then add them up. What if you have something below the x-axis? Like, what if you have something like this? What are you going to do now? Still find the area, right? But yeah, you do. So work with the area for each separate component. Triangle, rectangle, triangle, triangle, rectangle, triangle. You remember it's between the line and the x-axis. Add them together. What do you got to be careful of when you're adding these two together, though? Yep. Sorry? Yeah, these ones are negative, right? Okay, positive up here, negative down here, add them up. If you get a total positive, it means a momentum gained. If you get a total negative, it means a momentum lost. Now, what else can we do in conjunction with these F versus T graphs besides just finding the area and therefore finding the impulse? Remember, if we need to, we can also use this equation. That's part of half of the equation that appears on our data sheet. Why can we not use F times delta T? What's wrong with that one? Rosie? Yeah, like what force do we use, right? It's a changing value. So what value do we use? The F times delta T, it assumes constant or average force. Usually when we do a problem, the force is constant. If not, we're told the average force is whatever. Here it's constantly changing, so what number would we use? It's not practical to do it that way. All right? Okay, I want to give you a little question here and see what you can do with it. Okay, this is a little bit different, but I want you to still think the same way as I've told you to think. Just going to see if you can kind of extend this here a little bit. Right away, what are you thinking right now? Daniel? Okay, where's the title? Sure. Isaac, what are you thinking? Area equals impulse, right? I mean, sure, if you're plotting a graph, you need a title, and you need data on the graph, right? But first thing to your mind, when you see force versus time, I want you to be thinking area equals impulse. All right, I'm going to draw a shape here. It's going to be a triangle. Let me relabel this so I get some more space. I'm not going to label all the intervals down there. You can see what I mean here, right? 2.5 is where the peak is. 5 is where the where it ends, where whatever it is that's in contact with the object breaks contact with the object. I'm going to tell you here right now, I'm going to tell you that the impulse imparted to this object is 50. I'm giving you the impulse this time. The impulse imparted to the object is 50 Newton seconds. I want to know the maximum value of force. That's a little bit different, but I still want you to think about it the same way as we've thought about those other questions. Okay? Find the maximum value of force. Find this value right here. Okay, let's see what we can do with that for the next 90 seconds or so. And then we'll do it as a class. Let's have a look now at the question. We want to find the maximum force. Listen, if I was to cover this up, except for the picture, you don't know what you're being asked, right? What do you think? What do you think when you see that picture? Area equals impulse. It doesn't matter what you're being asked, you're still thinking area equals impulse. Now the problem is I can't find the area. That's okay. If you can't find the area, that's okay. I still want you to be thinking area equals impulse. Because you know, if you solve this question correctly, you know that that was the strategy that you followed, right? You still did area. You still involved the area. All right, what are we looking for? The maximum force. Well, the maximum force is the height of this triangle, right? We know the area this time. We know the area is 50 Newton seconds. We know the area equals the impulse, and we know its value is 50, and we know its equation is 1/2 base times height. We're going to say 50 is equal to 1/2 of the base of 5 times the height. There you go. 1/2 times 5 is 2.5. 50 divided by 2.5. 50 divided by 2.5 is going to be 20. Make sense? How many people got that? Good, excellent. So quiz tomorrow on the 3 aspects of impulse, right? The 3 things about impulse. Math, okay, the math of impulse, the qualitative predetermined versus non-predetermined impulse, and then of course our force versus time graphs. Got it? All right, let's take a look at some of the homework that we had last night, which was page 462, and then a little bit on page 467. Any issues with either of those 2 questions, please, on page 462? Yep. Yeah, we can. Number 1 says draw a graph of net force as a function of time. During the first 0.15 seconds, increases from 0 to 22. Okay, so this is question 1, force versus time. This is 0.15 seconds. 0.15 seconds, and the force is going from 0 to 22. So we're going to draw a line going up here from 0 to 22 in 0.15 seconds. And then it says during the next 0.25, it decreases to 0. The next 0.25 takes us to 0.4 seconds. So during the next 0.25 seconds, it goes down to 0. There's our graph. Using the graph, calculate the impulse. Well, area equals impulse. So we're going to say the impulse is 1/2 of base times height. It's going to be 1/2 of 0.4 times a height of 22, whatever that works out to be. And then finally, CS is for the speed of the ball when it leaves the shooter's hand. Whatever that is, we're going to set equal to m times delta v. So now that we've got delta p, and we've got m given to us in kilograms already, we can solve for delta v. Well, is that okay? Do you want to go through the numbers there? All right, let's have a look at number 2 then. A soccer player heads the ball with an average force of 21 newtons west for 0.12 seconds. Draw force versus time graph. Here's our force versus time graph. 21 newtons for 0.12 seconds. It's the same force for the entire trip. What's the impulse? I was going to say 1/2 base times height, but what is it this time? Yep, just base times height because it's a rectangle, right? So it's 0.12 times a height of 21, whatever that works out to be. Hey, anybody do this one a little bit differently? Not find the area? There is another option here, but I just assume you not follow it, but I'll mention it in case you did it. F times T actually works for this. You could, for this one, say delta P is equal to F times delta T. How come? Daniel? Yeah, because the force isn't changing here. If you multiply F times T, what are you really doing? Base times height, right? Force is height, time is base, so it's really height times base, but it's exactly the same thing, right? When the force is constant, it doesn't really matter. But to be honest, I just assume you go this way, because then at least it gets you in the habit of doing area equals impulse. And C, oh, this one's a little bit trickier, actually, C. What was the value for this one? Yeah, 2.52. Let's just double check that with our answers here. Yeah, okay, 2.52 Newton seconds. What are the other units that you could use, by the way, besides Newton seconds? Kilogram meters per second, good. All right. We want to find the mass of the ball. We haven't had to do that before. Well, what's the other thing we can do? M times delta V. It's the only other choice we have, really. Solve for mass. Delta P we already have. It's 2.52. And the mass here. Oh, wait a second here. Whoops, what's going on? Mass is not delta P over M. It's delta P over delta V, right? VF minus VI. We're going to say -2 subtract 4. What I really should have done is circled that before I did that question, right? Draw my attention to the fact that it's west. Draw attention to the fact that I got to make it a negative value. 2.52 divided by -6. I assume gives me the answer in the book, which is 0.52, 0.42. Yep. Mass is not a vector, right? That's right. That's right. Oh, wait a second. What's going on there, though? Why are we getting a negative value there? Why are we getting a negative value? Oh, I see why we're getting a negative value. Because what did I do? I didn't actually formally do this, but in reality, I did do this. 21 newtons west. What did I do with that? Yeah, I made it positive. So west is positive, right? See what I did? Wasn't even thinking about that, but west is positive. That would mean that technically it would be 2 minus -4, which gives me a +6, which gives me a positive 0.42. It's amazing, isn't it amazing how like the signs always work. They always work. Okay, if they don't work, it's because I've made a mistake somewhere, not because the math doesn't work or the sign conventions don't work. They always work. Okay? That's a good observation. That's a really good observation to recognize that, wait a second, there's a positive on the top and negative on the bottom. I should get a negative value, but I can't get a negative mass. So what's up with that? What we don't want to do is just say, oh, positive divided by negative, it's a negative, but drop the negative because it's mass, right? Think about why did I get a negative mass? I must have made a mistake somewhere. As it turned out, I still would have got the right answer there, but that's not always the case, right? When you see something like that, figure out what the mistake was, just in case you wouldn't get the right answer otherwise. Okay, good. Good there? Okay, the other questions were page 467, questions 1 to 5. Any issues with those questions 1 to 5 on page 467? Yep. 4, yeah. Any others? Going once, 5. Okay, number 4 says, what's the effect on impulse if the time interval is doubled if the net force is reduced to 1/3 of its original magnitude? This is variable value changing, right? This is variable value changing that we haven't done in the context of impulse, but we've done in the context of just straight momentum. You could see it any time this year with whatever equation we happen to be dealing with. This is my original impulse. It's equal to F times delta T. It's also equal to M times delta V, but the relevant equation of this is F times T, because you can see that I'm changing T and changing F. This is my original. I don't know what the number is. That's okay. What's my new momentum? Well, my new momentum, in the first case, A, if I'm doubling the time, F times 2T. Well, that becomes 2F times T, same thing, right? We don't know what the value of F times T is, but we know it's the original momentum. So I'm just going to say that my new momentum is twice my original momentum. Good? And number 4B, if the net force is reduced to 1/3 of its original amount. Here's the original momentum, the original impulse, I should say. My new impulse is equal to 1/3 F times T, but we know what the value of F times T is. We don't know what its value is, but we know that it's the original impulse, so we're going to say it's 1/3 of the original impulse here. I think I said up here it's twice the original momentum. It's not. It's twice the original impulse. Okay. And 5 says, even though your mass is much greater than that of a curling stone, it's dangerous for a moving stone to hit your feet. How come? You know what a curling stone weighs? About 20 kilograms. It's about 50 pounds almost. You got a 50-pound rock coming towards you. Why is it dangerous to stop it with your feet? Christian? Okay, so the rock, whatever speed you throw it at, is essentially going to be the speed that it hits your foot at, right? So why is that a problem, though? Why is that a problem, Ollie?
Because like if it hits your foot immediately, then that's the sort of time that it does. So the impulse does not change when it stops.
Okay.
So when the time is shorter, then the impulse force has to be larger.
Okay, so when that impulse, when that rock is thrown, we know that rock is going to stop sometime. Whether it hits the wall down at the other end of the rink or whether it hits your foot, it doesn't matter. That rock is going to stop somehow. And we know the impulse of that rock is going to be the same no matter how it stops. If you stick your foot in front of it, then that means it's going to stop probably fairly quickly. And if it stops fairly quickly, the force on your foot is going to be big. Small time, big force. Right? If you did want to stop it with your foot, what would you have to make sure you did? What would you have to make sure you did? Somebody said over here? Cushion it, right? How would you cushion it? Kind of cradle it, right? Let your foot go backwards a little bit. What does that accomplish? Yeah, you're increasing stopping time, you're decreasing the force. Make sense? We good there? Okay, I'm going to assign a little bit more homework for you for tonight. I'm going to give it to you now here. It's going to be questions 5 through 13. Okay, 5 through 13. Not going to give you a chance to work on that right now, though, although we may give you a chance a little bit later in class to work on that. What I want you to work on right now in class, a couple multiple choice questions. Starting with multiple choice number 7, somewhere around page 12 or 13 of your worksheet booklet. All right, let's have a peek at this question now. Question says, foundation piles for tall buildings are hammered into the ground using pile driver. Pile driver similar to the one shown below lists a 900 kilogram hammer. That's almost a ton, literally, a metric ton. A distance of 3.5 meters above the top of the pile, and then it allows it to drop. You guys have seen this before, whether you realize it or not. It's only been probably 3 or 4 years since they finished that massive interchange system at Deerfoot and Stony Trail there. You know what I'm talking about? And while they were constructing that, especially in the early stages, you saw this happening all the time. Even several months ago, the new interchange they're building at McLeod Trail and Shaughnessy, they were doing this. They hammer these like steel beams into the ground. They lift up a 900 kilogram hammer with a crane basically, and then they drop the 900 kilogram hammer onto this piece of steel. Drop it, bang. Lift it up, drop it, bang. Lift it up, drop it, bang. Lift it up, drop it, bang, and so on. Right? They keep doing that over and over and over again. And why do they do that? Because every time they drop that 900 kilogram hammer, it hammers that steel beam into the ground. What's the point of that? Well, when you build a bridge or an interchange or a big, tall building, it's heavy. And what do you got to worry about when you're building such a big, heavy thing? Tipping over, sure. Well, that's not the big thing about the beams that they hammer into the ground. Yeah, it could settle into the ground, right? It can settle into the ground. So they drive these things into the ground. Sometimes they call them friction piles. We drive these things into the ground. As they go further and further into the ground, it displaces more and more dirt, right? So as you displace more and more dirt, there's actually more and more pressure pushing in on these steel beams. As there's more and more pressure, there's more and more friction. So at some point, you've displaced so much dirt that there's so much friction acting on this steel beam that it becomes a really good support for something heavy. So you've got a good foundation, literally underneath this bridge system or underneath this building, because you've got these steel beams that are held in place by friction, literally held in place by friction, so they don't end up going up or down as the soil moves. So that's what we're doing here. We're lifting this thing up, dropping it down, and then we're hammering the pile into the ground. What's the magnitude of the impulse delivered by the hammer to the pile? Clearly, this is an impulse question, right? Because we're looking for impulse. So what do we got here? Well, we know we have a mass of 900 kilograms. Remember what I said earlier? We don't ignore givens. We just think about what's going on first. Then we look at givens. Something's 3.5 meters. What do you want to call that? Yeah. Call it the height, the initial height, or we could even call it the displacement. But the way that you guys seem to like solving these, call it the displacement. Make it negative 3.5 actually. The acceleration would be negative 9.81, right? Oh, wait a second, then it hits. There's two things going on here, right? There's two things going on here. The hammer falls, and then the hammer collides with the pile. This is information, this is givens for the fall. Let's do some givens for the collision with the pile. Well, we're looking for the impulse during the collision. I think that's all we got actually, isn't it? Looking for the impulse? Well, the mass stays the same, right? Okay, if we're looking for the impulse in the pile over here, let's say delta P is equal to, what, F times delta T, or, I don't know. I don't have force, or I don't have time, or I got mass, I don't have delta V. What do you want to use? Ollie, what do you want to do here? Good. That's what I would try first. Listen, though, if I happen to be wrong, it's okay. Try the other one. That's all. Don't worry about it. Like, it's a valid equation. If it works, great. If it doesn't, try another one. What's the mass here? 900 kilograms. What's delta V? VF minus VI, right? What's VI? What's VI? Yeah, good, 0. But it's not 0 because it was dropped from 0 up here. No, actually, sorry, it's not 0. It's not 0. VI is not 0. VI over here for the fall is 0. But during the collision, it's moving when the collision starts, right? So we don't know what VI is. But we know what VF is over here, right? How fast is it moving after the collision has taken place? Right. So we're going to say VF is equal to 0. All right. So basically, I guess we got to find VI here. How do we find VI? Any ideas? We did something pretty similar to this, I think, yesterday or the day before. How do you find VI there? Good. We're going to find the final speed here. VF squared is equal to VI squared plus 2AD. Anybody have the value of VF there? Someone's got to have that. What is it? Nope. Seems high, actually. 8 point. Oh, I got to square root it. So 8.2. Do you have that? 8.29. Okay, 8.29 meters per second. Don't forget to square root that. Right. All right. Then let's say it's actually negative 8.0 minus negative 8.29. When we do that, I want to say it's 7.46. Is that right? 7,460, but 7.46 kilonewtons. 7.46 times 10 to the 3. And it's positive. It doesn't just work out to be positive. It's positive because it should be. If the velocity is downwards, the impulse imparted to the hammer is upwards as the hammer stops, right? You got to apply an upward force. Good. How many people got that? Okay, good. Take a look at number 8, which is clearly related to that one. So what are we going to do for this one? It mentions impulse, but there's something bigger in there that tells me what to do here. Ollie? Gives you seconds, and what else is important besides seconds? Right, force and time, impulse, right? Force and time, impulse. We already found the impulse, right? We just found it. So let's say delta P is equal to F times delta T. We got impulse, we've got time, we solve for force. I'm not sure what that works out to be. Does anybody have that? Yep. 3.55? Agree? We would express that times 10 to the what? 6. So we would express that 3.55 because they're saying B times 10 to the W. It's the value of B, the base. It's 3.55. Not 3, not 4, not a one-digit answer. It's a three-digit answer, 3.55. All right.